Hello everyone, and welcome back to another exciting Grasshopper tutorial. Today, we will look into Grasshopper's workflow to model geometry based off lines. We will do this by remodeling the prominent panel structure of the ESOM building designed by the Bjarke-Ingels group. The expansion of the Eisenberg School of Management fascinates with its copper-clad panel structure. The geometry loops around the end of the existing Eisenberg building, but opens to the plaza at the same time by pulling one facade anchor to the rectangular campus axis. To recreate its structure, we first have to draw the base curves of this building, which define its overall form. As a first line, it's 3/4 of a circle, and as a second, it's half a circle, but with an attached line at the end. We will draw these circle segments with the arc command in Rhino, where we have to define the center of our arc first, then define our radius and draw about how much we want to draw. We need 3/4 of a circle, so this is the first one, and as a second one, we'll only draw half a circle, and then add a line at the end. We'll now go to the perspective to place the upper curve about 6 meters upwards, and we will now join the two curves below. So now our base curves consist of these two geometries. Now we will open Grasshopper. First things first, we need to reference these curves in our definition in order to work with them. To keep an overview of our definition, we will rename these right away. By clicking the symbol, we will make the name visible on the component itself. Here we go. As a starting point for the structure, we need to define all points where these panels will be placed later. We will do this on the lower curve, and we want to place them equally along the curve. The component we need to achieve this is divide curve. This will now divide the curve in equal parts, which count we can now define here. Let's say we have 90 panels. Now we have the placement of our panels on the lower curve. But if we do the same with the upper curve, we already realize that there are, because the curves do not have the same length, there are different spaces between the points on the upper curve and the lower curve. So that's not how we can do this. But we can use these points to find our points on the upper curve. The component to use is the perp frame component. The perp frame creates a plane on every point on a curve on a specified parameter. We have the parameters of our points right here, and we see these planes are always perpendicular to our base curve, which means the curve is our normal vector of the plane we created at the parameter. We can now use these frames as a plane to cut our upper curve with. The command can be found in intersection curve plane. Now all we have to do is define the curve we want to cut, which is our upper curve, and all the planes we want to cut with are these frames. Now we have a problem. as these planes are basically infinite, they do not only cut our upper curve right here where we want to, but also on the other side of this curve. But we can take a look in our list structure and see that for each plane, all the cutting points are collected in one single list. So to find our right points, we just have to choose the first cutting point with the upper curve. We can do this with a component list item, which lets us choose a value from a list by its index. As the first item in a list has always the index 0, which is predefined here, we can simply connect these two and now only have the first point of intersection, which is the point we want to have. We don't need the panel anymore. We can now connect these points with a line starting from the points on the lower curve to the points on the upper curve. We now see that our list structure is a bit messed up because the points on the lower curve are all in one list and the points of this curve are all in its own list. They will connect with every other point on the other line. So what we need to do is to flatten this input, and we have our connection lines. As we can already see, our viewport is a bit messed up. So we'll just blend out all of these and have our base structure right here. With these lines, we will now take a closer look at Grasshopper's data structure in lists. You already got to know the list item component, which lets us choose the value defined in a list by its index. These lists right here are all structured in branches. So we have this data tree, and this branch is a list, this one, this one, this one, and this one. So if we have a component, like the line component, which uses two data inputs to create this line, it always connects the corresponding branch and index of the list with each other. So we have our list structure here, and the structure of our points right here, and we already saw that if we connect these two now, we will get a really messy and complicated model. Because if one branch contains more data than another, Grasshopper will automatically connect each point of this list, or in this case this branch, with every point of the corresponding list, which is in this case the whole list, 90 points for this point. And then Grasshopper will do the next part of the list, which is the second branch, and connect it again with all of these points. What we did is we flattened our input here. So now we have the first point and the corresponding first point in this list. But we could also have done it other way around. So we wouldn't flatten this tree, but we would graft this other tree. Grafting puts each list in a single branch. So now we have the first branch in this list with its corresponding branch in this list, the one here with its corresponding branch here. It's easier in our case to work with a flattened list, however, because in this case we can work within this branch itself. So what we could do, for example, is take this list and shift it by 1. what this would do is it takes our points and sets each point one further. So the first item in our list would suddenly be the second item in our list, the second, the third, so on. If we wrap the tree, at the end, our last item will become our first item again. You can see it right here. We now have our second item as our first item in this list. How this would look if we now connected these two lists is that each point is not connected with its own point, but with the next point in the list, like this. We can blend this out. And our first point here is now connected with a new first point in the list, which is the former last point right here. And so now we have, this is our original first point to this original first point, but now it's shifted. So we connect it with this second point and so on. We could, of course, shift it even further, starting by 1, 2, 3, 4, 5. It goes on and on and on. When you're working with Grasshopper, you will soon have to manage this list and branch structure to create exactly the geometry you want. You already did it by creating these lines in the way you want to. And because of that, it's really important to understand how these lists interact with each other within every component. Otherwise, you might get some messed up results and don't understand why, or rather how it could be changed very easily. But let's go back to our beautiful ISM building. Now we want to extrude them to create this prominent panel structure. When we now type in the extrusion command, we see that we do have the base plane, but we do not have a direction yet. And the problem is the direction changes with every line we have here. We want to always extrude in the normal direction to this curve. So basically, we want to extrude on these perp frames, but always on our XY plane. How can we create these vectors? There is an easy way to find a normal vector in Grasshopper. The component evaluate surface will always give us the normal direction of a specified point on a surface. But the problem is we don't have a surface yet. So what we'll do is we will create a surface running through all these points and then selecting our point at this lower edge of the surface. To do this, we will use a command we already know from Rhino, sweep to rail. So we have our two rails as the lower and the upper curve. And as a section, we can use a line which is through the starting point of each of these curves. We will use the endpoint component, which will always find the start and end points of a curve. Connect the corresponding points and have the section we can run across these rails. By connecting it, we will create our surface. And now we can use this surface to get our normal vector. But there's another thing we need to define here. It is the point at which we want to get our vector. It's, of course, all along the surface. Every point on the surface has a different normal vector to the surface itself. So we already know which points we want. That are these points, but we need them to be defined on this surface we created. How can we do this? Well, we can just search for the closest point on a surface, in this case this surface and these points, and now we'll have every point on this surface that is closest to every one of these points, and we will have defined them in a UV definition which we need to type in our coordinates here. So when we are connecting these, we will see that we now have all these normal planes right here. If we want to visualize the vectors, we can always use vector display, which will use the direction and the anchor point to visualize in which direction our vector is going. So this looks exactly like what we wanted to do. So now we can take this vector and use it as our direction to extrude our baselines. Now we were a bit too fast, because by just plugging in our vector into the direction, they are unitized, but we can't define in which length. So we can't define how far our extrusion is going to extrude. To change this, we will type in the amplitude component, which will now take this vector, and we can define a length here. So we will just take 1.6 times the vector and connect it with our direction. And now we have the exact height we want our panels to be. Now we have nearly finished our panel structure. Basically, all we have left to do is to extrude our surfaces another time. Here we have the same problem as before, that we don't have one direction, but every panel has its direction on its own. This time though, we do not need the normal vector, but we need the tangent vector for each point of this line. And we are lucky, we already have our tangents defined with dividing the curve. So if we want to have a look at it, we see that for each point we already have the perfect perpendicular vector to the panel itself, in this case the tangent vector to the lower curve itself. So we will now use these tangents as our direction, but of course with a defined length. So we will once again use our amplitude component, and now can define how far we want to extrude our surfaces. Let's say they'll be around 30 centimeters. And voila, we have finished the ESOM building, or at least its main structure. So if we now want to see this in our usual Arctic view in Rhino, it's still just a preview of our Grasshopper geometries. But if we bake them, we basically save them as a Rhino geometry in the Rhino file. We have to choose the layer, and with this they are saved out of Grasshopper into Rhino. If we now change anything here in Grasshopper, it won't change the geometries in Rhino though. Now we can just blend out Grasshopper and take some beautiful pictures of the ESOM building. That's it for creating line-based geometry in Grasshopper. We hope you enjoyed this video, and if you are watching us as part of the course Computational Design Basics at the TU Darmstadt, please check if you have any new tasks on Moodle, and if you are watching us on YouTube, leave a like and see you next time.